Welcome to Geography 105, Weather, Climate, and You. This is Unit 14, Mid-latitude Cyclones.
If you put the title of the lecture together today, you'll see we are looking at large areas of low pressure that are basically traversing in the mid-latitudes of both hemispheres. In the northern hemisphere, these very large cyclones rotate in a counterclockwise fashion, whereas in the southern hemisphere, they actually rotate in a clockwise fashion, and we'll take a look at storms in both hemispheres. These are indeed very large weather disturbances or areas of low pressure that generally are associated with clouds, precipitation. If it's the wintertime, they're often accompanied by lots of snowfall and perhaps even severe thunderstorms on their southeast end in the northern hemisphere. So you're actually looking down on, this is a satellite depiction, infrared satellite depiction of a very strong mid-latitude cyclone on, I believe this was some October 30th, 1991, I believe, widely regarded as the perfect storm. And then we had another one in 1993, which we will take a look at later on in lecture. But these are just very intense areas of low pressure. Their central pressure being very, very low. Pressure gradient force is therefore enhanced and the wind speed is greater, which ends up just converging more air. So this is nothing more than a big kind of spiral or swirl of low pressure. And again, these are in the mid-latitudes, so we see these primarily in the areas from about, say, 35 to 45 degrees north or south latitude. Where the greatest mixing of the air masses is occurring. So you have CP air masses, MP air masses to the north, your polar air masses, mixing with your tropical air masses to the south. And the result of this mixing, these low pressures are basically tasked with mixing the very cool air in the polar regions of Earth's climate and the warm air near the tropics. So just a few facts here before we get into the nitty-gritty and kind of the more mechanics of these mid-latitude cyclones. In terms of our day-to-day weather here in the United States, they are the primary weather producers. So if you're talking about tornado outbreaks, snowstorms, any sort of rainfall, changes in the cloud patterns, drought, it's either due to these mid-latitude cyclones or, in the case of drought, the absence of a mid-latitude cyclone traversing the region. So these are very large areas of low pressure on the order of maybe 2,000 kilometers or so. And again, they're just relative areas of low pressure. So there's no definition of how low the pressure has to be in order for the storm to be a mid-latitude cyclone. It simply just has to be an area of like closed off isobars with some frontal features present that we'll talk about more here in a little bit. These mid-latitude cyclones can last up to weeks. I've seen them last for more than weeks. They can cover large portions of the continent. In the case of the superstorm or the storm of the century, the perfect storm, these low pressure systems can basically take up half of the United States at once. They bring abrupt, very sharp changes in wind, temperature, and sky conditions because of the frontal features that they are moving around. So these are kind of, these mid-latitude cyclones are very commonly associated with boundaries that we know as transition zones of air masses, which are fronts. And when those fronts pass by your location, you will see abrupt changes in sensible weather. One last thing about mid-latitude cyclones, they're stronger in the fall, winter, and spring, and not as strong or numerous in the summertime. And this comes back to the strength of the upper level jet stream. In forces in wind, we talked a little bit about the jet stream, and then we elaborated on that in global circulation. We talked about 4 jet streams across Earth's climate, 2 in the northern hemisphere, 2 in the southern. The northern jet stream in the northern hemisphere, which is the polar jet. We also have the subtropical jet that runs basically at around 30 degrees north. Polar jet, recall, runs at about 60 degrees north. When those jet streams are the strongest, which were when the ice attacks were the fastest, essentially occurred in the wintertime. That's when these strong storms are the strongest. That's when they are most common, most numerous, and that's when they basically bring about more abrupt changes in some of these weather features. So mid-latitude cyclones on the right over here, I have two images. One is a visible satellite depiction of a mid-latitude cyclone in its mature phase. The center of the low pressure system in this case was actually right over southwest Iowa. More of a schematic or conceptual, if you will, textbook model of what these mid-latitude cyclones look like would be down here in the bottom right, where we'd have some sort of warm front present here. You can see the cloud features associated with the cold front. Out ahead of the cold front, we have an advection of moist air, warm moist air, so this would be like maritime tropical air. Feeding in behind the cold front would be clear skies, no or very few clouds, sort of a CP air mass, continental polar air mass. And so you can see this mid-latitude cyclone, this area of a cyclone with frontal features, is just kind of a swirling mix in the bathtub, a vortex of these air of different densities. One thing that you can notice, sort of identification, if you will, pattern recognition of these from satellite, they almost have this comma appearance to them, where this is the tail of the comma and the head of the comma on satellite. That generally, when you see a comma-shaped structure like this, it's very indicative of a well-developed, mature mid-latitude cyclone. You won't always see mid-latitude cyclones looking like this. This is obviously sort of a textbook example, but this is one that is very well developed. We would call it in its mature phase. So we'll talk about the different life cycles and the stages of mid-latitude cyclone development here in a little bit. But this is what they look like when they're in the mature phase, so kind of at their peak intensity. They almost have this comma-shaped appearance on satellite, and you'll see more of this in your weather studies investigation manual assignments in this lecture, or after this lecture, excuse me. So they are responsible for the advection of different air masses, whether it be warm and moist MT air, cool and dry air CP, or cool and moist air MP. Another kind of textbook example of what mid-latitude cyclones look like in terms of their structure. Recall our fronts here. So we have a cold front that extends southwest of a surface low pressure. We have counterclockwise and converging winds around the low pressure system because we are in the northern hemisphere. We have a warm front that is basically draped to the southeast. And again, the circles kind of indicate, or the pips on these fronts, if it's a cold front, triangles, right? If it's a warm front, semicircles, they denote the movement of the air. So the warm air is trying to advance to the northeast. The cold air is trying to advance to the southeast. And so we kind of see these frontal features typically to the southwest and to the southeast of low pressure systems that develop in the northern hemisphere. To the southwest, again, we typically see a cold front. To the southeast, we see a warm front. And that would make sense, right? If we have a cyclonic or counterclockwise circulation around this low pressure, if you have northwest winds, that is going to be ushering in cooler air out of Canada, your sort of CP air masses. You can imagine if we had a low pressure here and winds on this side of the cyclone, we're drawing air up from the Gulf of Mexico. That would be very warm and moist air, and so it would create this boundary, if you will, our sort of warm sector down here in between the warm front and the cold front. And so you can kind of see why the fronts set up the way they do. It's because of the advection of the air of different source regions. Here's another really well-developed mid-latitude cyclone from visible satellite imagery, and you can see, again, the comma-shaped feature. In fact, this image is not even an animation, and you can still kind of get a sense that if I were to animate this, it would be a big swirling sort of vortex comma shape. And that is indeed the mid-latitude cyclone. Here's the cold frontal feature. We have the warm, moist air advecting out. You actually have thunderstorm activity across Tennessee. And believe it or not, snow was falling in this particular example in Minnesota. So these are very important in terms of day-to-day changes in weather. Obviously, if you're on this side of the front, your moisture and temperature characteristics are going to be quite different than if you were somewhere in Arkansas on this day and the cold front has passed through your location. So these mid-latitude cyclones, again, especially in the fall, the summer, and the spring, are really the main driving forces for day-to-day changes in weather. Mid-latitude cyclones were developed from a theory. This theory started in the early 1800s. It was called polar front theory. We'll talk a little bit about the person who developed polar front theory, Wilhelm Bjerknes, in just a second, the next slide. But it really wasn't until the early 20th century that we developed a better understanding of the conditions necessary for these cyclones to sort of enhance and sort of grow and go through life cycles and stages. And honestly, it really wasn't until the late 1970s when we had satellite data that we were really confirming a lot of our theories, and observational sort of analysis was guiding some of these conceptual theories that were in place since the early 1800s. So one of the main driving factors behind this and sort of any new scientific discovery is often war. War, for several reasons, is often the driver between the reason why we do, whether it's astronomical sort of observation, meteorological observation in the case of World War I or World War II, forecasting for deployment of troops and special operations forces. But a lot of the numerical weather guidance and prediction this is very true also in terms of the space race. In fact, if you've ever read Neil deGrasse Tyson's book, it kind of brings this to the forefront of discovery and scientific discovery being driven by war, and making the case that we should be doing it anyway. But oftentimes war often brings about these very strong pushes from federal agencies to develop technology. And this cyclone model was driven out of the ability to sort of forecast these abrupt changes in weather that we were seeing through observation. So here's Wilhelm Bjerknes. He basically developed this idea of the Norwegian cyclone model, and he called his theory of development polar front theory, because he was seeing these mid-latitude cyclones develop in the vicinity of the polar front jet stream, which is, again, at about 60 degrees north and 60 degrees south latitude. Sometimes, I think your Weather Studies Investigation Manual calls this the Norwegian cyclone model. It was developed out of the Bergen School of Meteorology in Norway, so it kind of gets and really Norway, believe it or not, was the forefront of the development of many meteorological principles in the late 1800s and the early 1900s. Since Wilhelm Bjerknes's polar front theory, we've made some tweaks, but it's very interesting. A lot of what Wilhelm was theorizing and seeing in observations really holds water today, and there are really only minor changes to Wilhelm's thinking when it comes to the way a mid-latitude cyclone goes through its life cycle. So you can see here the very beginning or birth of a mid-latitude cyclone happens as we have opposing air masses sort of butting up against one another. Neither of them are advecting, so they're not moving back or forth. We simply have this stationary front present where warm air is sort of butted up against cold air. So you might have something like an MT air mass butted up against a CP air mass, and a little disturbance may ripple across this sort of stationary front, and all of a sudden a kink forms. And when a kink forms, you have the birth of a mid-latitude cyclone because there is advection. We're going to talk about advection here in a minute. This over here on the left, there is actually no advection occurring during the stationary front principle, but as soon as a kink forms, we have advection. We have warm air advection and cold air advection, and I'll explain this a little bit more in our isothermal analysis coming up later on in this lecture. But I want to go through the stages first and then talk a little bit more about why these stages occur. The satellite pictures that I've been showing you have been from the mature stage, where we achieve maximum intensity. You can see now we have a well-developed cold front, a well-developed warm front. We have advections going on. We have warm air advecting north. We have cold air advecting south. Our mid-latitude cyclone is really feeding off of the instability of the different air masses. And finally, this cold air will travel a little bit faster, as we talked about in fronts and air masses. It will catch up with the warm air, and we come up with an occluded front here, which is not drawn in purple, but it should be. We have an occluded front up here to the north, and sort of the cold air charging and cutting off the warm sector, if you will. As soon as the occlusion process begins, this is really the death of the mid-latitude cyclone, and you will see the surface pressures begin to rise, and the general intensity of the low pressure system start to wane. Here's a list of facts about extratropical frontal cyclones, or mid-latitude cyclones, or frontal cyclones. You'll hear a lot of different names for these. I simply call them mid-latitude cyclones. They are large areas of low pressure that traverse the mid-latitudes. I think that's probably the easiest way to think about them. More of a scientific name would probably be extratropical cyclones because they are outside of the tropics. We do have tropical cyclones and hurricanes, which we will talk about in 2 more lectures after severe storms. But these are extratropical, so they are outside of the tropics, meaning they're in the mid-latitudes, and they do have fronts. We will see that hurricanes do not have fronts. So there are some main differences between mid-latitude cyclones and hurricanes, which we will talk about. So just some general facts. Let me walk through these with you. Mid-latitude cyclones are low-pressure systems around 30 to 60 degrees latitude. The winds blow counterclockwise in the northern hemisphere, clockwise in the southern hemisphere, but both terms would be cyclonic. They spiral into the low at the surface, so we have converging winds. When that air converges, it cannot go into the ground. It can rise and form clouds of precipitation. Mid-latitude cyclones form at the intersection of fronts, i.e. stationary fronts. We typically have a cold front to the south and the west, warm front to the south or the east of the low. After the cold front passes, we typically have cold air behind it, warm air ahead of the low pressure system. So that's the idea of advection, which I'll show you more on in just a second. Low pressures and high pressures both move in the direction of the jet stream winds. There will often be thunderstorms ahead of the cold front prior to its passage. A lot of times, as we've seen in fronts and air masses, as these cold fronts advance, they lift warm, unstable air ahead of them and can form convection in severe thunderstorms. Oftentimes, there will be steady precipitation ahead of the warm front as the air is slowly rising up and over the cooler, more dense air. This is often why we get ice storms. The cloud sequence of warm fronts are often cirrus, cirrostratus, altostratus, nimbostratus, as we talked about in the fronts and air masses lecture. And the life cycle of low pressure systems actually look like a sideways version of a breaking ocean wave. In fact, you kind of see this if you really have to think about this, but if you turn a mid-latitude cyclone sideways, sort of look at it as a cross-sectional perspective, you see this breaking sort of curled over ocean wave. Perhaps in the next lecture I'll kind of show you an animation to help you visualize that. The energy source for these mid-latitude cyclones, you might be asking yourself, well, I know they're stronger in the wintertime, so there has to be something to do with wind. And yes, the wind does feed off the temperature changes, the temperature gradients. So the real energy source for these mid-latitude cyclones are the fact that the cold air wants to be under the warm air, and we have this sort of battle of the air masses going on where the cold, dense air wants to trade places with the warm, less dense air, and the warm air that wants to rise. And so it feeds off of sort of this idea of what we call baroclinic instability, or instability developed with temperatures. This whole idea of a formation of a mid-latitude cyclone is termed cyclogenesis. You'll see this word several times in your Weather Studies Investigation Manual. The definition for cyclogenesis is the formation of a mid-latitude cyclone. So genesis, to begin, cyclone, the genesis of a cyclone, the formation of a low pressure, basically. There are some important ingredients necessary for cyclogenesis. So why don't we just have low pressure systems all the time? Well, cyclogenesis kind of needs certain ingredients. Just like if you were baking a cake, you would need certain ingredients, flour, water, sugar, etc. You also want particular ingredients when you're trying to form these strong low pressure systems. We need frontal boundaries between air masses of different character. Something like this temperature surface map. We have warm, moist air butting up against the cold, moist, cold, dry air, and you can see sort of probably where the location of the cold front would be. 73 in Little Rock, 44 just northeast of Tulsa. There's a big change in temperature there. There's probably a cold front present. So these cyclogenesis will feed off of it's sort of its source of energy is this difference in large differences in air masses, and you can imagine it's right along these frontal features. In order to maintain cyclogenesis, we must have upper level divergence, so air diverging away. Because when air diverges in the upper levels, we know it will converge in the low levels, and that's what we want for low pressure systems. Baroclinic instability is this idea of temperature or air masses of widely different temperature and dew point butting up against one another, and the idea of vorticity, or having some sort of pre-existing spin in the atmosphere. Vorticity is a special kind of fancy word for spin or movement in a fluid, basically the rotation rate in a fluid. And if you get some of that area already, you can imagine if you start spinning a fluid already or give it some existing rotation, it can maintain itself. So if you put all of these together, why do we care about cyclogenesis? It's really because at the surface of the Earth, if you're trying to forecast the weather and abrupt changes in weather, if you want to forecast snowstorms, severe weather, or any sort of high-impact weather events, you want to be able to forecast where these mid-latitude cyclones are and where they might move. So we know the upper levels and the surface are inherently connected and linked, and we're going to show some animations here about the upper levels sort of guiding the surface low pressure system and how it will sort of feed off of it all in this synergistic three-dimensional way that is very hard for introductory level students to sort of wrap their mind around. But if you're really good at thinking in 3 dimensions and you have an idea of this 3-dimensional conveyor belt model that I'm going to show you coming up, you're going to have a really easy time understanding of what's really happening in 3 dimensions as these low pressure systems traverse from west to east across the United States. So, how do we get upper level divergence? Well, we need to go back to this idea of a big ridge trough pattern, or this meridional type of jet stream flow that we talked about. We had 2 types of flow across the United States. We had sort of west to east, what we called the zonal flow, and more of a north-south component, meridional flow. When you get that really north-south big changes in the jet stream from north to south, we call those long waves, LW. Carl Gustav Rosby came up with this idea of long waves. And he kind of named them after himself. I talked about this already, the Rossby wave, the series of ridges and troughs encircling the globe at mid to high latitudes. And at any given time across the northern and southern hemispheres, we typically have 4 to 6 of these ridge trough, ridge soft systems. And they are so important because they basically govern through super and subgeostrophic flow where high and low pressures are going to form at the surface. If you have an upper level trough, you're nearly guaranteed to have a low pressure system east of that trough axis. Here's the trough axis running north and south. To the east of the trough axis, we know the winds slow down subgeostrophic and then go supergeostrophic around the top of the ridge. So we have speed divergence. The air is, right, we come out of the toll booth, the air parcels accelerate, they create upper level divergence, that causes surface convergence and basically evacuation of mass aloft, and the air must fill that from below. And so you spin up this low pressure system at the surface, and we say wherever there is upper level divergence present, that is a formation or a very necessary mechanism to have a mid-latitude cyclone present at the surface. So really, these variations in the geostrophic wind are gradient wind, if you will, super and subgeostrophic flow leading to areas of upper air convergence and divergence. And again, that really, we know the upper level is really governing what's going on at the surface. Now, embedded in these longer waves, so here's a great example of a long wave trough. That's the big orange trough axis that I have driven in here. So here's kind of the long wave ridge, long wave trough, and another long wave ridge. But you can see embedded in this long wave, we have very small sort of ripples or what we call short waves within that. I've denoted the short waves by smaller trough axes here. You can kind of pick out 3 of them. We have one here up in the Hudson Bay area. We have one traversing across Iowa. We also have one moving into the Four Corners region. So these are very small sort of long waves embedded in a much bigger long wave. That's why we call them short waves. These short waves often kick up sort of smaller areas and more localized areas of low pressure that can have their own little frontal features. So we might have a big mid-latitude cyclone, but we might have several areas, maybe 3 areas of distinct low pressure at the surface. We call these waves. Sometimes you'll hear people call them pieces of energy. I really don't like that term. I much rather prefer a short wave trough. That's really what they are. They're a trough of short wavelength or short amplitude compared to its much bigger long wave counterpart. If you put all of these 3 together in sort of an application slide here, if you will, in the upper left I have an animation of water vapor imagery. I have a 500 millibar height map in the upper right, and I also have a surface map from the Weather Channel on the bottom right. I'd like to start with the surface map from the Weather Channel first. You can see we have a very distinct area of low pressure with several closed-off isobars off the east coast of the United States. We have our cold frontal feature. We have our warm frontal feature. Just as your guess, you would probably suggest that this mid-latitude cyclone is mature. It is in its mature phase. We do not have occlusion yet. The cold front has not caught up with the warm front. On mid-latitude cyclone, we can see this kind of well-developed comma-shaped nature. You can almost see exactly where the cold front would be located. This is the very dry CP air that's filtering in behind it. We have very nice colored warm MT air. Recall that in the water vapor, we are looking for areas of water vapor in the mid-levels. So this is indicating a very dry stream of air in here. What we're going to call our dry conveyor belt here in just a moment. We have our warm conveyor belt out ahead of that. That is the stream of MT air from the tropical regions, and we have our dense CP air sort of filtering out of Canada in here. Our 500 millibar height map indicates a very large long wave trough on the eastern coast of the United States. We have a very large long wave ridge in the west. So ridge in the west, trough in the east typically means cold for Chicago because we have big counterclockwise rotation around the low pressure system driving northerly winds across the east coast and the Midwest. That typically means cold air advection for places like Chicago, Indianapolis, Columbus, and Pittsburgh. We get that very driving high pressure and low pressure together, sort of a pinwheel, if you will, gears driving that cold CP air out of Canada. And you can see here in this animation, the air is definitely sinking from north to south, bringing cold air advection to the east coast of the United States. A couple slides ago, I mentioned this idea of advection with isobars, and then I'd talk a little bit more about it in a slide. And this is the slide that I want to kind of bring up, the idea of advection. Okay, so what I have here in the bottom right is essentially an isotherm. Okay, so a line of constant temperature. I have two of them, two isotherms. I have the 20 degrees C isotherm and the negative 25 degrees C isotherm. I also have 500 millibar height lines, but you can also think about these simply as lines of pressure. So the pressure gradient force says high to low, go to the right. If we have geostrophic flow, we'll end up with wind that blows parallel to the lines of isobars, or lines of height. In this case, if we're in the northern hemisphere, we developed a wind from left to right. As the wind accelerates from high to low, the Coriolis force directs it to the right. So that we end up with this westerly wind at points 1 and 2. However, if we had a wind blowing from left to right in this image, if you were at location 2 and air at location 1 is coming toward your location at location 2, you would suggest to me that air at location 1 is the same temperature at air as location 2. Isotherms are lined up parallel to isobars. And therefore, the location, air temperature at location 1 is the exact same at air temperature at location 2, and as air is advected or moved horizontally from location 1 to location 2, we really have no change in the temperature after some period of time at location 2. And so we have no advection. We basically ask ourselves, if we were allowed the wind to blow for an hour, would the temperature at location 2 change? And the answer to that is no. Because if this is 20, this is negative 25, the air temperature at location 1 is probably something like negative 26. And the air location at 2 is also probably about negative 26. And so after some period of time, if the wind is blowing directly parallel to that iso line, that isotherm, the air at temperature 2, at location 2, will never change temperature. And if it never changes temperature, we are under the assumption that we have a barotropic condition. Barotropic is simply a fancy word that means no advection, where the change in temperature with respect to time, kind of go back to our d banana d time example, only this time we're talking about the change in temperature with time. So d big T over d little t, how does the temperature change with respect to time? The answer to that question is 0 in a barotropic condition, meaning that there is no change in temperature with time. If you were to go outside and sit for 5 hours, the temperature would not change. That is a barotropic condition. In a barotropic condition, we will have isotherms, the dashed lines, parallel to isobars, the white solid lines on this particular image. When isotherms and isobars cross, however, we get advection. Okay? Because now imagine yourself standing at my mouse cursor, and after some period of time, we have wind that is blowing across the isotherms. At my mouse cursor, we have warm air advection. Because if I were to sit here for some length of period of time, I have a southerly wind blowing towards my mouse cursor. The air from the south is warmer than the air at my current location, and therefore warmer temperatures should be coming to my location after some period of time. Temperature will be increasing with respect to time. This is a baroclinic atmosphere. So we either have barotropic, no advection, or baroclinic, an atmosphere that is suggestive of advection. So at my mouse cursor after some period of time, we would expect the air temperature over here to rise. On the other hand, if I'm sitting over here and I have a northwest wind, that is bringing air at lower isotherms or colder temperatures. After some period of time with a northwest wind at this cursor location, I have cold air advection, and I would experience temperatures falling over some period of time. So you have to look at the wind direction or your isobars, because we know those will line up relatively nicely. If we have isobars and isotherms that cross at any angle, there has to be some sort of advection, and therefore we assume that the atmosphere is baroclinic. Now, in your Weather Studies Investigation Manual, you will be looking for warm and cold air advection based on the crossing of isobars and isotherms, and they will simply ask you at different cities, do you see warm or cold air advection? Okay, so let's take a look here. There's another practical example. This is an example from late 2005 of a low pressure system that was pretty much smack dab over Chicago. We had kind of two short waves, so we ended up with two low pressure systems on the weather map. One near Chicago, one near probably International Falls area. And you can see the snow falling on the radar here across Wisconsin and Iowa. We had some rain, some showers, thunderstorm activity along the cold front in places like Kentucky, Tennessee, Mississippi, Alabama, even into Louisiana. And then north of the warm front in the Great Lakes region and the Canadian border, we also had some very cold rain and some snow showers falling in that area as well. And look at the, simply just kind of take a second and look back and forth, some pattern recognition as to where the features on the surface map sort of line up with the current temperature map. And you can see, and here's your nice warm empty air mass here to the southeast. We have temperatures in the upper 60s and low 70s. If you cross the front into places like the Central Plains, they are under the influence of very strong cold air advection. We have these counterclockwise winds. We know that the winds here should be out of the north because of our counterclockwise flow. And in places like Missouri, Iowa, Nebraska, and Kansas, we are experiencing really cold temperatures and cold air advection, with the fastest winds probably being over central Iowa because the spacing of the isobars is so close together. Warm air advection over here, as we know, our counterclockwise rotation bringing up warm MT air from the Gulf of Mexico. And so you can sort of see the structure on the surface map up here in the upper left as related to the surface temperature plot in the lower right. So you can see why it is so important to forecast where these mid-latitude cyclones are and where they're going. You can imagine a day in Omaha and a day like this is quite different than a day in Pittsburgh. And so depending on where you are relative to this mid-latitude cyclone, these frontal features is really not only going to determine your temperatures for that particular day, but also your chances for snow or perhaps even severe weather. So here's the schematic example for the cold air advection. Ignore the pages down here. This is for the in-class folks for their particular textbook talking about warm and cold air advection, so you can ignore the C pages here. But this baroclinic does go for all of you, Wa and Ka, warm air advection or cold air advection, depending on what type of advection, which way the isobars and isotherms line up. In example B up here, we have cold air advection. If you are standing at location 4 and waiting for air at location 3 to get to you, because the air is moving in this direction, we have colder air coming towards you because this is a lower isotherm. And so if you, over the course of time, cold air would be coming towards your location. We call that CAA or Ka, cold air advection. Down here at location 6, we have air of location 5 coming towards you. Air at location 5 is only -20 versus the -25 that you're experiencing. Warmer temperatures are coming to your location with respect to time, and therefore you would expect the temperature to rise over the next couple of hours. So short waves kind of cause this kink, or the disturbance in the flow. They eventually create baroclinic conditions, advection, if you will, which is really the birth and leading into the maturity of these mid-latitude cyclones. So how does this all play out? If we were to put this all together, consider the dynamics that are going on, which are a little bit of a step above this particular class, but just talk a little bit about the basics of what's going on from start to finish. Okay? We have some sort of a short wave disturbance moving through a long wave in the atmosphere aloft. This short wave causes a little bit of upper level divergence and causes a little bit of kink going on in the stationary boundary. This kink creates baroclinic instability and starts advection on the east side and cold air advection on the west side. So we start a baroclinic atmosphere by having warm air advection in the east and cold air advection in the west. These in turn create areas of low pressure on the east side near the warm air advection and cold air or high pressure on the west side of the cold air advection at the surface. Eventually, we will get to maturity as the wave cyclone develops, going through its entire life cycle, finally occluding from the surface, and we create a cold pool and closed circulation aloft. So, what the heck does that look like in terms of an animation? I found this animation online. I think it does a great job sort of showing what's going on. I'm going to show this first in the two-dimensional view, and then we'll go ahead and take a look at the three-dimensional view. So, starting off, I'm going to pause this here really quickly. We have a low-pressure system that's forming on the leeward side of the Rockies, somewhere like Guymon, Oklahoma, just north of Amarillo, Texas. This low-pressure system has a cold front to the southwest, a warm front to the southeast. Here's the general path it's going to take because of the upper-level Rossby wave. So it is going to pass directly over Chicago in this example. As I allow this to animate, you'll see the cold air will move a little bit faster. We still have this general counterclockwise flow around the low. And as soon as the cold air begins to catch up, we begin to have an occluded front form, and the occlusion sequence has begun. So now this little eyeball is focusing on the box here. What I would like you to do, I'm going to play this animation over. Let's take a look at what this looks like in sort of 3 dimensions, focusing in on this little area just near the surface low. So as it animates, the cold front is moving faster and faster and faster. You can see the warm sector, which is this very small area right here, is being basically shunted off. As soon as those two meet, we get an occluded front, because the cold air has now caught up with the warm air, and now we have, again, remember this is cool air at the surface, so warm fronts, remember, are sloped back toward colder air. And so as the cold air goes deeper and deeper and deeper into this, we basically have a boundary between cool air to the north and cold air behind it. The cold air will always be on the bottom because it's more dense. We have warm air aloft, and so we probably just have sort of cloudy rain showers left over. There's really not much left in terms of any temperature change at the surface, but aloft we can still get showers and storms with these occluded sort of features. So I'll play that through one more time to let you see what that looks like. We just talked about the vertical structure of these mid-latitude cyclones being underneath the greatest of area of upper level divergence. So this is just a slide to remind yourself that when we do have upper level divergence, that will be the preferred area for a surface low pressure system to form. When we have strong upper level divergence, which is again more air being taken out aloft than is being brought in at the surface low pressure will intensify by dropping, and it'll converge more air at the surface, create a greater isobar field, more packing the isobars, create a faster wind, converge more air to fill the void of the air being left in the upper level jet stream. So a simple way to remember this for the exam is to simply tell yourself, when the outflow above exceeds the inflow below, the surface low is sure to grow. And by grow, I mean intensify or drop in central pressure. So when upper level divergence exceeds surface convergence, the surface low pressure system will drop, intensify, grow, strengthen. All of those are synonyms in this case. Your chapter 10 is a little bit different than the in-class chapter 10, so again, please ignore the bottom here case study. This is not in the Weather Studies Investigation Manual, at least the April 15th, 1994 example is not. In your Weather Studies and Investigation Manual, you'll be looking at a different case study, so you can pretty much ignore this, so I just wanted to have this in here. We can go through this really quickly, but you can see a nice, well-developed mid-latitude cyclone over central Wisconsin. Cold front, warm front, showers and storms sort of lining up here. This is just a case study of a very strong cyclone in 1994, but we see very strong cyclones like this every single year. A big upper level trough, surface low pressure system forming in the area of greatest upper level divergence. On satellite, it had this nice, great comma-shaped appearance. Here's another example from 2005. Big upper level trough, low pressure system forming in the area of greatest upper level divergence. This one passed just to the south of Chicago, brought a tornado outbreak across the Mississippi River in places like Louisiana, Mississippi, and Arkansas, while snow fell in Des Moines, Iowa that particular day. Another just general reminder here, we have a zonal flow on the left, meridional on the right. We said meridional, just a refresher, a review, is the stormy pattern because this creates accelerations in the flow, super and subgeostrophic, creating upper level divergence and convergence. Okay, finally here I want to focus in on the families of cyclones that we sometimes see across the hemisphere. Again, these kind of look like Cinnabon cinnamon swirls, A, B, C, and D. These are the large areas of mid-latitude cyclones. You can almost see which ones are mature and which ones are just in their birth or decay phase. C is definitely in its decay phase. You can see it's already wrapped up several times, so it is already occluded. D is in its nice mature phase. It looks like a nice comma structure. B has already probably occluded once and is beginning to decay. And A looks like it is now starting to go through some sort of decaying feature. So we can often tell where these mid-latitude cyclones are based on their life cycle, just kind of by looking at their satellite appearance. But these are, again, very strong areas of low pressure that are moving across the mid-latitude systems. And sometimes they form in these families, these frontal boundaries that are draped across the United States for several days. And so this was kind of funny. Last year at College of DuPage in the wintertime, we had several days where we were getting Monday off classes for snowfall. And it's actually because a family of cyclones just happened to be impacting us at a periodicity of about 7 days. And so every Monday we had this big chance for a snowstorm, and it just so happened that these family of cyclones were spaced out about 7 days apart. And so sometimes that's why you see getting into a very repetitive weather pattern, especially in the fall and the winter, with these mid-latitude cyclones coming every so often as their family, if you will, a succession of these cyclones sort of impacts the same region every 5, 6, 7 potential days as they go through their life cycle. So we often see that in the fall and the winter as well. This is not a two-dimensional feature. We know that. You've seen this already in the three-dimensional animation. But you need to appreciate something called the conveyor belt model when talking about mid-latitude cyclones. These are not two-dimensional entities. They are three-dimensional. And the conveyor belt model helps students wrap their mind around the explanation for this comma-shaped cloud pattern that we typically see. This is an example of the conveyor belt model in 3 dimensions. So the surface low pressure system would be at the surface up here at the intersection of the cold and warm front. We would have a conveyor belt of warm, empty, moist air that would slope back towards the colder air, so it would be advected over top of the warm front. Recall that warm fronts are sloped back towards the colder air. Cold fronts have more of a slope because of the friction. We talked about this. And so they are very efficient at lifting parcels along their leading edge. And we typically have a dry conveyor belt that we find in the mid-levels of the atmosphere that really never surfaces. It's just always present in sort of the mid-levels, and the air is typically a very low water vapor content. And I'll show you a satellite animation of that right here. This is the storm of the century, which is a storm that happened on March 19th, 1993. Many of you are probably too young to remember the storm of the century. If you do remember the storm of the century, or you may ask your parents about the storm of the century, they'll probably recall that the Florida Panhandle had 1.5 feet of snow from this particular storm. There was snow all through Georgia and the Carolinas. There was also a big tornado outbreak the day before in Florida. We had a very large sort of nor'easter type of snow event in the Northeast. And I thought this example was really great because it shows not only the great comma-shaped appearance of this mid-latitude cyclone, but also sort of the conveyor belt features that were present here. We had a warm conveyor belt that was flowing from south to north. So here's the cold front, the warm conveyor belt, which is advecting moist air towards the north. We have a dry conveyor belt in here, so you can see there's really no cloud features, or at least very tall cloud features. We have no colors showing up on the infrared. We call that the dry slot, or the dry conveyor belt. And then the cold conveyor belt that sort of wraps around the low pressure system, creating this head of the comma that often brings lots of snowfall in the wintertime with it. So again, we're looking at two-dimensional satellite images, but it is indeed this sort of three-dimensional conveyor belt model when you actually sample these mid-latitude cyclones with weather balloon observations. You can see that very nicely. Here's another great case from 2005. We've had recent examples, 2010, 2011, of these very strong mid-latitude cyclones occurring. 2014, we haven't had any yet as of this lecture recording. I'm sure we are on our way to experiencing a few mid-latitude cyclones upcoming here in the winter season. This particular case from 2005 exhibited a low-pressure system developed just north of Des Moines, Iowa, with an occluded front that it went towards Chicago. And really, Chicago was kind of the triple point, the intersection between the warm front, the occluded front, and the cold front. And we had some thunderstorms going on along the cold front. We actually had a warm front with a really funny pattern that was really not able to advance northward because of cold air damming in the Appalachian Mountains. So the Appalachians extend here. The warm air was really just not able to force itself on this particular day up and over the Appalachian Mountains because of all the cold, dense air that was already in place due to cold air damming. But you could see this is a very big, disruptive low-pressure system. They were canceling flights in the Dakotas, Minnesota, Nebraska. We had flight delays from severe weather in the southeastern United States, visibility problems with fog in areas that were receiving cold air damming, and really the entire two-thirds of the eastern portion of the United States was under the influence of this low-pressure system and seeing a sensible weather impact at the surface. Before you got, the only places that really weren't being experienced by this were places out in the Intermountain West, and they were already dealing with another mid-latitude cyclone that was beginning to come on shore. So on surface weather maps, and again, this is from November, so you can see we are in that sort of fall-winter period where these mid-latitude cyclones are most numerous and sort of well-developed. All right, you might be asking yourself, can anywhere in the United States experience these mid-latitude cyclones? The answer is yes. However, there are three major areas where these cyclones form, and they form there due to topographic features. Within the United States, we kind of have three areas. We typically have low-pressure systems that we call Alberta clippers in the wintertime that develop on the foothills of the lee of the Rocky Mountains in the province of Canada of Alberta. We typically have Colorado lows that form on the lee side of the Rocky Mountains in southeast Colorado, northeast New Mexico, northern Texas, and the panhandle of Oklahoma. And we also have what we call Cape Verde lows, or lows that typically traverse across the east coast of the United States. You may have heard these called nor'easters before. Typically originate cyclogenesis forms in the Gulf of Mexico, and then it feeds up this baroclinic difference between the warm conveyor belt on the eastern United States, the Gulf Stream, and the cold air over the eastern United States, and sort of makes a hook northward. These are sort of preferred or preferential areas of cyclogenesis in the United States, and we often see low pressure systems sort of form there and track there in sort of a preferential pattern. Here is some research that was done several years ago looking at the frequency of cyclogenesis, or the birth of systems, in both the summertime in the upper left and the wintertime in the lower right. And you can see we sort of have these bullseyes, one of the bullseyes being, especially focused down here in the wintertime, a preferred area here in sort of Alberta, a preferred area east of the lee of the Rockies in Colorado, and sort of another preferred area or bullseye here in the east coast of the United States of cyclones developing in these three regions. And again, the track these particularly take, Alberta clippers can come down and influence Chicago. Oftentimes they kind of take this northwest to southeast track across the Great Lakes. Colorado lows often take sort of a hook shape or a panhandle. We call them sometimes panhandle hooks. They come out of the eastern New Mexico, eastern Colorado area and sort of hook up into the Great Lakes. And then these nor'easters, oftentimes when we get these really amplified jet stream patterns, can ramp almost due north up the east coast of the United States. And again, these are taking a westerly fashion because of the the predominant or preferred winds in the mid-latitude regions. We know in the mid-latitudes of both hemispheres we have westerly cyclone tracks that is totally different than tropical cyclones that we'll talk about in not the next lecture, but Unit 16, where we see tropical activity that influences the United States actually comes from Africa, traversing east to west across the Atlantic Ocean before influencing the United States. And again, this is because of the predominant easterly direction of the winds in the tropical regions. As we get into the mid-latitudes, we know we have the mid-latitude westerlies that generally move the wind and weather patterns from a west to east fashion. All right, one more thing I want to define here, because the Weather Studies Investigation Manual mentions rapids or intense cyclogenesis. We call these really intense cyclogenesis sort of mechanisms, or when this does happen, we give this the term bomb. And an explosive area of cyclogenesis is called a bomb. This is when an extratropical cyclone or mid-latitude cyclone develops very rapidly. And in order to be considered a bomb, the central pressure of a mid-latitude cyclone must drop 24 millibars in 24 hours. So we must see a decreasing rate of pressure at 1 millibar per hour in the central pressure. If we see a deepening of 1 millibar per hour and it sustains itself for 24 hours, we will give that cyclone the name or the term a bomb. Bombs typically bring about very abrupt changes in sensible weather conditions and can often be the leading cause for very intense snowstorms and very intense severe weather outbreaks when this mid-latitude cyclone is going underneath or undergoing a very unique, rapid intensification of its central pressure. So as this low pressure deepens very rapidly, we see a very strong response in the wind fields at the surface. So we see very strong advection, and we see very strong winds then due to the strong advection, and creates very rapid changes in sensible weather conditions at the surface. Bombs, this explosive cyclogenesis, will occur when we have a very unstable air mass in place. Maybe a very, very cold air mass butted up against a very, very warm air mass. So the more sort of baroclinic instability that we have present, the more likely we are to have this bomb situation where explosive cyclogenesis can take place. Okay, again, there is seasonal variation in this cyclone intensity. I'm not going to beat this dead horse, but these mid-latitude cyclones are developed in more, so we see more numerous mid-latitude cyclones and stronger mid-latitude cyclones in the northern hemisphere winter. We also see more developed mid-latitude cyclones in the southern hemisphere during the southern hemisphere winter. So our storms in the United States are better developed and more frequent in the coldest months because the jet stream is indeed the strongest, and we know there is a direct relationship between the strength of the upper level jet stream, the amount of divergence and convergence that's happening in the upper levels, corresponding to the surface weather features that we see. So these mid-latitude cyclones will move with the upper level jet stream. In this case, we know the surface low pressure system is going to move in a northeasterly direction because the upper level winds are basically going towards the northeast. Okay, these cyclones will follow the area of greatest baroclinic instability, and they will move in the areas of greatest upper level divergence. So as this upper level trough moves, the surface low will also move with it, basically at a sort of a rule of thumb here. The surface weather features will move at about half the speed of the winds at 500 millibars. So basically what you do, you launch a weather balloon, you figure out the 500 millibar winds. If they're 40 knots, the surface low pressure system will move at about 20 knots. And again, we see this sort of time and time again. This is sort of an old rule of thumb of forecasting, that if you want to forecast where the surface low pressure system is going to move, is Chicago here? Are we going to be influenced by the cold front, or are we going to be influenced by the snow on the backside of the low pressure system? Well, look at the upper level winds and give yourself a guesstimate of where the surface low should be tracking based on the direction of the upper level winds. So here's the rule of thumb. Winds at 500 millibars steer the surface, and the surface speed is about half that of the 500 millibar level. So if you want to try your hand out at forecasting, you can pull up 500 millibar maps that you can find on the Weather Maps link wall that I've provided in the course menu of Blackboard. You can find the 500 millibar maps in there and then kind of follow along the progression of the surface maps as the upper level 500 millibar features move, and you can see that the surface low pressure systems will indeed move at generally about this speed of the rule of thumb, which is half that of the 500 millibar velocities. Okay, so I hope this particular unit was a little enlightening for you, and if you have particular questions, again, make sure to email me or plan a Skype meeting with me. I think after you do the Weather Studies Investigation Manual assignments for mid-latitude cyclones, you'll have a little bit greater appreciation, get your hands sort of in the data of exactly what's going on with these low pressure and cyclone features, and you can really start to get an idea of why they're so important to forecast due to their very extreme or high impact on our day-to-day weather here in the United States.